In the complex world of construction project management, understanding scheduling is crucial. Effective scheduling ensures projects are completed on time and within budget. A key concept in scheduling is total float. This essay will explain total float and its importance. We will explore its calculation and benefits. Total float is the amount of time a task can be delayed without delaying the project completion date. It represents the flexibility within the schedule. Project managers use total float to make informed decisions about resource allocation and task prioritization. Total float is a powerful tool for managing project timelines. Understanding its calculation and application is essential for project success. By effectively utilizing total float, project managers can mitigate risks. They can also optimize resource allocation, leading to more successful project outcomes. Total float, also known as slack, is the buffer time available for a task. It is the leeway a task has before impacting subsequent tasks or the project deadline. Identifying and managing total float are essential aspects of effective project scheduling. Consider a scenario where a task has 5 days of total float. This means the task can be delayed up to 5 days without affecting the following tasks or the project's overall completion. Project managers can use this float to accommodate unforeseen delays, allocate resources strategically, or make necessary adjustments to the schedule. Having a clear understanding of total float empowers project managers to make informed decisions. They can prioritize critical tasks, allocate resources effectively, and ensure the project stays on track. By carefully monitoring and managing total float, project managers can enhance the likelihood of delivering projects on time and within budget. Construction projects are complex, involving numerous interconnected tasks, materials, and stakeholders. Unexpected delays are common. Weather conditions, material shortages, or contractor issues can all impact project timelines. Total float provides a buffer against these uncertainties. It allows project managers to absorb some delays without derailing the entire project. By identifying tasks with significant total float, project managers can create contingency plans. They can adjust schedules and allocate resources to critical path activities. Furthermore, total float helps optimize resource utilization. Resources can be allocated more efficiently by understanding which tasks have flexibility in their start and end dates. This prevents bottlenecks and ensures that resources are available when needed for critical tasks. There are two primary methods for calculating total float: the early start, early finish (ESEF) method, and the late start, late finish (LSLF) method. The ESEF method determines the earliest possible start and finish dates for each task, assuming all preceding tasks are completed on schedule. To calculate total float using the ESEF method, subtract the early finish (EF) date of a task from the early start (ES) date of its successor. The difference represents the total float for that particular task. For example, if Task A has an EF of day 5 and its successor, Task B, has an ES of day 10, the total float for Task A would be 5 days. 10 minus 5 equals 5. This indicates that Task A can be delayed by up to 5 days without affecting the start date of Task B. Let's consider a simplified example to illustrate the ESEF method. Suppose we have a project with 3 tasks, A, B, and C. Task A precedes Task B, and Task B precedes Task C. Here are the early start and finish times. Task A, ES equal sign, day 1, EF equal sign day 3. Task B, ES equal sign day 4, EF equal sign day 7. Task C, ES equal sign day 8, EF equal sign day 10. Using the ESEF method, we can calculate the total float for each task. Total float for task: A equal sign ES of task B, EF of task, A equal sign 4, 3 equal sign 1 day. Total float for task B equal sign ES of task C, EF of task B equal sign 8, 7 equal sign 1 day. Task C has no total float because it's the final task. Any delay in Task C will directly impact the project's completion date. The late start, late finish, or LSLF method determines the latest possible start and finish dates for each task without delaying the project's overall completion. It works by back-calculating from the project's deadline. To calculate total float using the LSLF method, subtract the late start date of a task from the late finish date of its predecessor. The difference represents the total float for that task. For instance, if Task X has an LS of day 15 and its predecessor, Task Y, has an LF of day 10, the total float for task X would be 5 days, 15 minus 10 equals 5. This means task X can be started as late as day 15 without affecting the project's end date. Let's revisit our previous example with tasks A, B, and C. This time, we'll use the LS-LF method to calculate total float. Assume the project's deadline is day 10. Here are the late start and finish times. Task A, LS equal sign, day 1, LF equal sign day 3, task B, LS equal sign day 4, LF equal sign day 7, task C, LS equal sign day 8, LF equal sign day 10, using the LS-LF method. Total float for task A equal sign LS of task A, LF of its predecessor, none in this case, equal sign 1. 0 equal sign 1 day. Total float for task B equal sign LS of task B, LF of task A equal sign 4. 3 equal sign 1 day. Again, task C has no total float as it directly determines the project's completion. Utilizing total float offers several benefits in construction project management. It provides flexibility in scheduling, allowing project managers to adjust to unforeseen circumstances. If a task with total float experiences a delay, it's less likely to impact the critical path or the project's overall completion. Moreover, understanding total float helps optimize resource allocation. Resources can be shifted from tasks with significant float to tasks with less or no float, ensuring that critical path activities are prioritized and adequately supported. Effective use of total float also empowers project managers to make informed decisions regarding task prioritization, resource leveling, and risk mitigation. By maximizing the utilization of available float, project managers can enhance project efficiency and increase the probability of on-time and within-budget project delivery. The concept of total float finds practical application in various construction project scenarios. For instance, consider a highway construction project. The task of laying asphalt requires favorable weather conditions. By analyzing the schedule and considering potential weather delays, the project manager can identify the total float available for asphalt laying. If the float is significant, the manager might choose to wait for favorable weather without impacting the overall project schedule. However, if the float is minimal, the manager might employ contingency plans, such as utilizing quick-drying asphalt or scheduling additional crews to work extended hours, to mitigate the risk of delays. In another scenario, a delay in the delivery of structural steel for a high-rise building project could significantly impact the project timeline. By identifying tasks with total float, such as interior finishing work on lower floors, the project manager can reschedule those tasks. This minimizes the impact of the steel delivery delay and keeps the project progressing. While total float is a valuable tool, its mismanagement can lead to project delays and inefficiencies. One common issue is the student syndrome, where tasks are delayed until the last possible moment, consuming all available float. This leaves no buffer for unexpected issues, increasing the risk of delays. Another issue is the lack of clear communication and understanding of total float among project team members. If subcontractors or suppliers are not aware of the critical path and the importance of adhering to deadlines, tasks with minimal or no float might be delayed, impacting the entire project. Furthermore, failing to account for external factors, such as weather conditions or material availability, can lead to inaccurate total float calculations and overly optimistic schedules. This can result in a false sense of security and ultimately lead to project delays when these external factors inevitably come into play. Mastering the concept of total float is crucial for efficient construction project scheduling. By understanding the methods of calculating total float and its implications for task prioritization and resource allocation, project managers can navigate the complexities of construction projects more effectively. Total float provides the flexibility to adjust to unforeseen circumstances, optimize resource utilization, and make informed decisions regarding risk mitigation. When effectively utilized, total float can be a powerful tool for keeping projects on track, within budget, and delivered on time. However, it's important to remember that total float is not a license to delay tasks unnecessarily. Mismanaged total float can lead to the student syndrome, inaccurate schedules, and ultimately project delays. Clear communication, realistic scheduling, and a proactive approach to risk management are essential for harnessing the true potential of total float and ensuring successful project outcomes.